Sorting a list is often an important prerequisite to doing other useful things on it. For example, one way to search for whether a list has duplicates is to sort it and then check if any adjacent values in the sorted list are equal to each other. So our goal is to arrange a list in ascending or in descending order of values. So let's just focus on ascending order, because obviously descending order everything will be symmetric using greater than instead of less than. So understand a basic algorithm for sorting. Let's try to sort a pack of cards. So here is a simple way to sort a pack of cards that many of us are used to in practice. We start with the top card and we start forming a new pack of sorted cards. So since the top card is a single card, by definition the new pack is currently sorted. Now we take the second card, and depending on its value with respect to the first card we picked up, we either put it above or below. So continuing in this way, we'll take the third card and put it in the appropriate position with respect to the first two cards, and then insert the fourth card in the appropriate position with the first three cards, and so on until the entire stack is sorted in place. So since we keep inserting each new card into an already sorted list of the previous cards we have built up, this algorithm is quite naturally called insertion sort. So to describe insertion sort in Haskell, the first function we need to write is the function insert, which puts an element into a sorted list. So concretely, let us assume we are sorting integers. So insert takes an integer and a sorted list implicitly of integers and produces a new sorted list with the element we just added put in the correct place. So the base case is to insert a value into an empty list, which just produces a one element list consisting of that value. On the other hand, if we want to insert x into a non-empty list of y's, we look at the first value and check whether or not x should come before it. If x is smaller than the smallest y, then we just stick it up front. If x is not smaller than the smallest y, then overall between the x and the y's, the first y is the smallest value. So we pull that out in front and recursively insert the x into the remaining y's. So this in general could require us to push x all the way to end of the list. So if we take the input size of insert to be the size of the list into which we are inserting, it's clear that the worst case complexity T of n is big O of n. Now we can express insertion sort in terms of this auxiliary function insert that we just used. So if we want to sort an empty list, then we have to do nothing. So we just get the empty list back. If we have to sort a non-empty list, then we first sort the tail. Okay? And having sorted the tail, we insert x into it in the appropriate position. So the insert function does all the work. An alternative way to write the same thing is to say that we fold the insert function from right to left. So if we start with a list x0, x1 to xn minus 1, then we start with the empty list and then we insert xn into this and we get xn. And now we'll take xn minus 1 and insert it into this, then take xn minus 2 and insert it into this, and so on. So we're just folding this insert function from right to left. So a concise definition of this recursive function is just use our function foldr and say that isort is foldr of insert. So what is the complexity of insertion sort? Well, for the empty list, right, T of 0 is 1, because in one step we get back the empty list. And for the non-empty case, we have to first sort n minus 1 elements, and then having sorted n minus n elements, we have to insert a value into this list, which takes order n time, because remember that the complexity of insert is order n. And therefore, the recurrence for insertion sort says that T of 0 is 1 and T of n is Tn minus 1 plus On. Now we have seen this recurrence before, and we know that if we expand it out, we will get T of n is On squared, because we will get something like 1 plus 2 plus 3 up to n. So can we do better than O(n) squared for sorting? So here is a better strategy which is called divide and conquer. So what we do is we take the given list and we divide it into two halves, right? And then we separately sort this half, the left half and the right half, and then we combine the two sorted lists into a single overall sorted list. Okay? So the final step requires us to combine two sorted lists L1 and L2 into a sorted list L3. Now this is easy to do because this, again, imagine that you just had, say, two stacks of cards or papers or whatever sorted top to bottom. Now you look at the top card in each thing and move the smaller of the two to the new list, right? And each time you keep looking at the top card of the two and move it to the smaller of the two. So in other words, if we are looking at lists, we look at the first element of both lists and move the smaller of the two to the new list and keep continuing until we have exhausted both the lists. Right? So this is called merging. So we are merging two sorted lists into a single sorted list. So here is an example of how it would work. So note that this is L1, so this is sorted. 32 is smaller than 74 is smaller than 89, and this is L2. So this is also sorted. So we start from the left, we are looking at the leftmost element. So since 21 is the smaller of the two, we remove it from the second list and move it to the new list. Now since 32, now we are comparing 32 and 55, then we look at the smaller of the two, which is 32, and move it to the new list. Continuing with this, we now move 55 because we are comparing these two elements. We get 55 and then 64. And now, of course, we have nothing left in the second list, so we can actually blindly copy the first list. So we copy 74 and 89. Right? So this is the merging procedure. And now our earlier divide and conquer strategy was to sort the first half, sort the second half, and merge. Just remember that this notation means extract the ith element. Okay, so it says sort from 0 to the midpoint and from the midpoint to the end. So this should be a round bracket. Okay, so we sort from 0 to n by 2 minus 1, from n by 2 to n minus 1, and merge the sorted halves into a new list L prime. And how do we sort the halves? Well, we use the same strategy. Again, we divide those into two and then we merge them and so on. So let's run through how merge sort would work on an arbitrary list. So at the first step, we will divide at the midpoint. So we will divide this into two lists and try to sort them recursively. So we will get the left list and the right list. Now in turn, we will divide each of these into two because we are applying the same strategy. So we get two lists from the left and two lists from the right. Now we pretend that we still don't know how to sort. So we will move it one more step. So we will split each of these lists of length 2 into 2. So we will get individual lists of length 1. And now remember that a list of length 1 is by definition sorted because it's only one value, so it must be in order. And now we can start merging, right? So we want to merge these two, merge these two, merge these two, merge these two to get merged lists which are sorted of length 2. So we will merge 43 and 32, we get 32 followed by 43. The second pair gives us the same list as before. The third pair again gets inverted and the fourth pair gets inverted. So now we have sorted lists of length 2 after merging lists of length 1. Now we merge these sorted lists of length 2 to get two sorted lists of length 4. And finally, we merge the two sorted lists of length 4 to get a sorted list of length 8. So this is how merge sort works. We divide until we get singletons, and then we work backwards, merging until we get back a final sorted list. So let us now write merge and merge sort in Haskell. So first we write the merge function. The merge function takes two lists which are implicitly assumed to be sorted, right, and produces a new output which is the combination of the two sorted lists. So we have base cases. If the first list or the second list is empty, we can just copy the other list without doing anything because it's already sorted. We just tag it along. On the other hand, if we have something to do, okay, and both lists are non-empty, then we look at the first element, okay, and if the first element on x is smaller than y, then we merge the tail, okay, which is the x's with the remaining y's, and then we stick x as the new first element of the overall list. So x is the smallest overall. If x is not the smaller one, then y is the smallest overall. Right? So this is a very direct translation of our merging strategy that we saw before. So to analyze merge, one way to think about it is that every time we apply the second rule, okay, we are in principle adding one value to the final output and reducing the number of elements to be merged by one. So overall, it will take as much time as the number of elements in the two lists put together. So we can say that the complexity of merge is big O of n, where n is the sum of the lengths of the two input lists. Once we have written merge, then merge sort is immediate. So merge sort of the empty list is the empty list. Merge sort of the one element list is the one element list. And merge sort of any element list with two or more elements consists of first recursively sorting the first half and the second half, which are defined in terms of taking half the elements. And remember that take and drop supplied with the same argument exhaustively enumerate all the elements. So take plus plus drop is always the list itself. So we can be sure that we are not losing any elements or missing out or duplicating any elements. We are taking the length of L with integer divided by 2, and then we are dropping the same number of elements and using that as the back half of the list. And having now constructed the sorted versions of the front and the back, we are merging them. Okay, it's instructive to note that we need this case. We can't just do with a base case of empty, because otherwise, if we take merge sort of x and we don't have this case, supposing we don't have this case, then we would try to split it into two. So this would become merge sort of the empty list and merge sort of x again. Now this would give us empty by the base case, but now this would again go back to the same case. So we will end up with a loop. So we need a base case for the empty list, but we do need a base case for the singleton list as well. Otherwise we will end up with an infinite loop when we come to the singleton and try to split it into back and front. So the analysis of merge sort is slightly more involved than what we have seen for the function so far. Okay, so let us, since we keep dividing by 2, it's convenient to assume that the original list is a power of 2. So let's assume for simplicity that the original list we want to sort is of length 2 to the k for some integer k. Then the recurrence for merge sort says that in order to merge a list of length n, we have to merge the front and merge sort the front and the back. So we have to solve two subproblems of half the size, and then merging takes linear time, the sum of the two input lists. So once again we can use unwinding to solve this recurrence. It's just that the expression is a little more complicated than we had seen for the earlier ones. So t of 1 is 1 and t of n is 2 tn by 2 plus n. So now we recursively expand 2 tn by 2 and we get 2 tn by 4 plus n by 2. And we will combine these 2's and rewrite this 4. So we will write this 2 times 2 as 2 square. We will write this 4 also as 2 square for a reason that will become clear in a minute. So now we expand this n by 2 square and we will get another division by 2. Right? So we will get 2 times t n by 2 cube plus n by 2 square. Now notice that this and this cancels. Okay, so we get another n. We already had 2n. Right? This n plus 2n times n by 2. So now we will have 3n. Okay, and then 2 squared into 2, this product will give us 2 cubed. So after 3 steps, we have 2 to the power 3, t n by 2 to the power 3 plus 3n. So now we see a pattern emerging that this is 3 steps, and we have a 3 here and a 3 here and a 3 here. So you can check that if you do this j steps, you get 2 to the j, t n by 2 to the j plus j times n. Now this keeps going until this becomes 1. When does this become 1? So n by 2 to the j is equal to 1. That means 2 to the j is equal to n. In other words, j is the log of n to the base 2. Right? So when j is log of n, then n by 2 to the j is 1. So we get t of 1. So at this point we have 2 to the log n, because j is j is log n, plus 1 times log n, okay, plus n times log n rather, because we have got j times n, right? So now j is log n, remember. Okay? So we have 2 to the log n from this term. We have t of 1 plus log n times n, and t of 1 is 1, so this goes away. So we have 2 to the log n plus log n times n, which is 2 to the log n by definition is n, so n plus n log n, but then this is a smaller term, so we throw this away and we get O of n log n. Right? So merge sort takes time, O of n log n. We should remember that log n is a much smaller function than n. So O of n log n is actually a function which is much closer to O of n than to O of n squared. So merge sort is a significantly more efficient sorting algorithm than insertion sort or any other order n squared sort. So we can avoid this merging if we don't have to move elements between the left half and the right half after dividing the list into 2. So can we ensure that everything on the left is already smaller than everything on the right? Then if we sort the left and we sort the right, we just have to stick them together. So suppose the median value remember is the value such that half the values are smaller and half the values are bigger. Suppose the median value is m. Right? Now if we take all the values less than or equal to m and to move it to the left, and then we have half the values greater than m on the right and sort them, then because m is the median value, the right hand side lies strictly to the larger side than the left hand side, so we can just use plus plus to combine these two from left and right. Okay? So I don't have to do any merging. Now the problem with this strategy is that it requires us to know the median, and the standard way to find the median would be to sort the list and to pick up the middle element, but our aim is actually to sort the list, so it's kind of circular to say that we are going to sort the list by finding the median. So instead we will do this kind of splitting of the list with respect to some arbitrary value. We won't use the median exactly, we will just pick up some value in the list and divide it into values which are smaller than this pivot and larger than this pivot. Right? So we pick up some value from the list, call it a pivot value, okay, and split the list with respect to this pivot element. So this algorithm is called Quicksort, and it is due to Tony Hoare. So you choose a pivot element, typically the first value in the list. You partition the list into lower and upper parts with respect to the pivot. So the lower part is everything smaller than or equal to the pivot. The upper part is everything greater than the pivot. And now you sort the two parts and move the pivot in between. Okay? And once you sort the two parts, the pivot in between, everything is automatically in order. So typically this is how Quicksort would work. Right? So you start with some arbitrary list, and then you pick the first element, say, as the pivot. Now you analyze the rest of the list and decide which ones are to the left and which ones to the right. So here, for instance, the yellow values 33, 32, 22 and 13 are smaller than the pivot, and the green values are larger than the pivot. So you rearrange the list so that all the smaller values are to the left and all the larger values are to the right. And now assuming that you can recursively sort those two, so you can sort the yellow and the green thing to get an overall sorted list. Quicksort in Haskell is extremely easy to write. So quicksort of the empty list is of course the empty list. If I have a non-empty list, I pick this as the pivot, right? So here it's called the splitter, but it could be also called the pivot. And then I take list comprehension to take all the values which are smaller than or equal to the pivot and all splitter, and all those which are greater than the thing. Now, one important thing to note is that list comprehension is operating on the tail of this list. So the actual splitter, though it is less than or equal to itself, is not being included in lower. This is crucial, otherwise we'll end up, as you might imagine, into a situation where the list has a duplicate value, because we are going to put back the splitter here. So if the splitter is both in lower and it's there on its own, then we have a problem. Okay? So what we do is we take strictly those values excluding the splitter and we divide them into the lower and the upper. We recursively sort them using Quicksort, and then we put them into place. So we have the lower list, okay, and then we have the splitter, and then we have the upper list. And because the lower list is smaller than the splitter and the upper list is bigger than the splitter, no further merging is required. The problem with this strategy is that we have no control over what value is at the beginning or wherever we choose the pivot. So if the pivot happens to be the largest or the smallest value in the list, then either the lower or the upper will become empty. So then the recursive call to sorting lower and upper is not n by 2 but could be n minus 1. So we may end up with a similar recurrence to insertion sort, which says that in order to sort a list of n elements, we have to first split it. So notice that splitting requires us to walk down the list and move things to lower or upper. So that splitting phase requires order n time, and then we may have to recursively sort something which is as large as n minus 1. And of course we know that if we expand this out, we get this 1 plus 2 plus summation up to n, which is order n squared. So paradoxically, an array which is already sorted, for example, where the first element is the smallest value, is a worst case input because it's the smallest value and it will split the list as size 0 and size n minus 1. So it appears that Quicksort has not achieved anything because we have got a worst case complexity which is as bad as insertion sort, the first naive sorting algorithm that we discussed. Now it turns out that Quicksort or sorting in general is one of the rare situations where we can actually compute the average case, and the average case for Quicksort turns out to be order n log n. So let us just quickly look at what it means to compute the average case. Okay? So for sorting, notice that the actual values that are being sorted are not so important as their relative order. So we can always assume that if we are sorting a list of n elements, that the elements are actually 1 to n, and the actual list given to us is some permutation of 1 to n. So therefore the space of all n element inputs effectively becomes the set of all permutations of 1 to n. And now we can assume that each of these is equally likely. So we can assign a sensible probability to each input, saying it's 1 by n factorial. And now we can calculate the running time across all these permutations, and using standard probability theory, although it involves a bit of calculation, you can actually show that the expected running time, which is the average that we are looking for, is big O of n log n. So this is why it's difficult to do in general, because for sorting we can kind of exhaustively characterize all the inputs of size n, but for more complicated functions it may not be so easy to do this, and it may not be also so easy to assume a uniform distribution over all possible inputs and so on. So to summarize, sorting is an important starting point for many functions on lists, so it's good to be able to sort a list efficiently. Insertion sort is a natural inductive sort, but its complexity in the worst case is order n squared. Merge sort, on the other hand, uses divide and conquer and has a complexity of order n log n. Quicksort is a bit simpler than merge sort because we don't have to have a merge step. We divide the things according to a pivot element and then we just paste the resulting list together. This has a worst case complexity of order n squared, but you can actually show that Quicksort has an average case complexity of order n log n.